To get a sense of scale in the universe, it helps to start close to home. Earth gives us a baseline, but the smallest objects that share properties with stars are large gas giants like Jupiter, the heaviest planet in our solar system and about 11 times the size of Earth. This chart plots physical size against mass. You might assume that if you took 90 Jupiters and smashed them all together, you would create a massive, sprawling object. But as you continue adding mass, the physical volume actually flattens out. Instead of growing outward, the object packs that extra material tighter and tighter. The internal pressure rises until it hits a critical density threshold, generating enough heat to force nuclear fusion to ignite. Even after they ignite, true stars like red dwarfs and our own Sun remain surprisingly compact. The Sun contains over 99.8% of the mass in the solar system, yet holds all that material within a tightly constrained sphere. In these early, stable stages of a star's life, gravity is relentlessly pulling inward. Because that gravitational crush is so dominant, sheer mass is a terrible predictor of physical size. To see exactly how far that rule holds, we can look at R136A1. At 315 times the mass of our Sun, it is the heaviest known star in the universe, burning with a blinding intensity 9 million times brighter than our own star. Looking at this scale comparison, you see our tiny Sun, the massive weight indicator showing 315 times the solar mass, and the result, a sphere barely 30 times wider than the Sun itself. A star this massive burns at extreme temperatures. This heat generates aggressive stellar winds, violently blowing away gas that could let it accumulate volume. If the heaviest, hottest objects in the cosmos actively blast away their own material to stay compact, how do the actual giants of the universe exist at all? As long as a star is stable and healthy, its own crushing gravity and furious energy output physically restrain it from expanding. To build the largest objects in the cosmos, you can't just add more material. You have to kill them. As a star exhausts its core hydrogen fuel, the core contracts, becoming denser and hotter. This triggers faster nuclear fusion. The sudden surge of internal energy pushes back against gravity, forcing the outer layers to swell drastically outward. Our own Sun will go through this exact process. When its fuel runs low, it will expand to 200 times its current radius, easily swallowing the inner planets in our solar system. Attaining unimaginable size is a direct symptom of structural collapse. For the most massive stars in the universe, this dying phase turns them into hypergiants. They inflate to such extreme proportions that gravity at the surface becomes too weak to hold the outer layers together. The intermediate stages include blue and yellow hypergiants. The Pistol star spans 300 times the radius of the Sun, while Rho Cassiopeiae reaches 500 times that size, burning brightly enough to be seen with the naked eye from thousands of light-years away. But the absolute peak of stellar volume belongs to the red hypergiants. Our current record holder is Stephenson 218, estimated at a staggering 2,150 solar radii. Placed in the center of our solar system, Stephenson 218 would instantly engulf Mercury, Venus, Earth, Mars, and Jupiter, stopping only at Saturn's orbit. Even at the speed of light, a photon tracking its outer edge would take 8.7 hours to complete one lap. Pushed to physical limits, the star ceases to act like a dense object. It becomes a loosely connected, fragile sphere of gas bleeding into space. Getting precise measurements on these behemoths is difficult. Because they lack the gravity to hold themselves together, they are constantly blowing themselves apart, shrouding their true edges in thick, chaotic stellar winds. That means Stephenson 218 is just our best current estimate. As our instruments improve, the title of the universe's largest star will remain a blurry, moving target. Regardless of their exact dimensions, the fate of these dying stars is identical. They will shed huge amounts of mass, accumulate heavy elements deep within their cores, and finally detonate in a core collapse supernova. That violent detonation returns all of those newly forged heavy elements and gas back out into the surrounding galaxy. The most expansive objects we can observe are not permanent fixtures. They are fleeting moments of destruction, required to seed the universe with the materials for the next generation of stars.